Hello guys, today we'll be talking about uh, rotational mechanics, which is topic 8.4 in the IB Physics HL syllabus. Be careful because this is only an HL topic, so SL students won't be examined on this topic. So what is rigid body mechanics? Rigid body mechanics is basically Newton's laws and the normal mechanics, but in rotational motion. For example, take a pen. Let's assume this line is a pen. If you apply a force such as this on the right and apply an opposite force on the left with the same magnitude, by Newton's laws, you'd think that it would stay in equilibrium since the forces act in opposite direction and are in equal magnitude. But that's not the case. If you take any pen or anything like this line, the object will actually start to rotate. And this is what we'll be seeing today. This force applied at a distance r, for example, let's say this is a distance r, is known as torque. Torque is equal to the product of force times r. So force we know is in newtons. But what is r? Well, r is the distance from the pivot point. So what is a pivot? Let's say you have a door. The pivot point of the door is to the left, which is the opposite of the handle. So the distance from the handle to the pivot point is r. So when you apply a force on a door, let's say 10 newtons at a distance 50 centimeters from the pivot, you are applying a torque of 10 times 0.5, since we use meters, equals 5 Newton meters. So torque is the force applied at a distance r from a pivot point. And let's get back to the pencil. I apply a force F here to the right. So usually the pivot point would be the center of mass, and in most IB questions, uh, you'll not be given the actual pivot point, so you must assume that the pivot point is the center of mass. Since here the pencil center of mass is right here. So let's say this is 0.1 meters and this force is 15 meters. So the torque applied would be 15 multiplied by 0.1 equals 1.5 Newton meters. So again, torque is in Newton meters and it is the force applied at a distance r from the pivot point. Now, just like you had Savat equations in normal mechanics, we also have Savat equations for rotational mechanics. So I'll be telling you what are the rotational equivalents of the of velocity, displacement, time, and acceleration. Or time is the same, of course. So let's start with displacement. Displacement in normal mechanics is denoted as S and is in meters. Its equivalent is theta. As most of you know, theta is a Greek letter used for angles, and this is, of course, since we're talking about rotation, we're talking about angles. Theta, also known as delta theta mostly here, because it's the change in the angle, is in radians. Based on where you are in your math syllabus, if you don't know, a radian um, is a unit of angle measurement, such as degrees, but here we'll be using radians only. If you don't know, and to convert from from degrees to radians, you multiply by 180. No. You multiply the angle in degrees, so say 45 degrees times pi divided by 180, which will give you 45 pi over 180, which can be simplified to pi over 4. radians. Now we have velocity. Of course, velocity in meters per second, its equivalent is angular velocity, which you would have seen in circular motion. So it's denoted by the Greek letter omega, and its units are radians per second, written like this. Now we have the final thing, acceleration. So denoted by A in normal mechanics, it is in meters per second squared. In rotational mechanics, it's known as angular acceleration, as denoted by alpha, and it is in radians per second squared. So these are the things you must know. Displacement in rotational mechanics is delta theta in radians, velocity is omega in radians, and acceleration is alpha in radians per second squared. Now let's go on to the Savat equations. So the Savat equations are the exact same. Nothing different. The only things that different that instead of, for example, displacement, you'll be using theta. Instead of velocity, you'll be using omega. And instead of acceleration, you'll be using alpha. So, for example, the first equation says delta theta, which is the change in the angle, equals omega final plus omega initial divided by 2 multiplied by time. And this is the exact same as the normal Savat equation, which states that the displacement is equal to the velocity, final velocity, plus initial velocity divided by 2 times time. The only thing that's not different here is, of course, time. So this equation is basically telling you the average velocity, since you're taking the final initial and dividing it by 2, or the average displacement, sorry. This equation, you won't be using it a lot in IB exams, in my exam, and many past papers. You won't be seeing this equation a lot, but it's okay to know it, and you'll know it if you know what theta, omega mean. You'll probably be able to use it in any situation. Now let's go to the other equation that states that the final angular velocity equals the initial angular velocity plus alpha, which is the angular acceleration multiplied by time. This is also the equivalent in normal mechanics to velocity final equals the initial velocity plus AT. Yeah, so it's the exact same. This is also one of the ones that you won't use that much. I haven't seen many questions using it, but the next two are the ones that I see many questions on in both normal mechanics and rotational mechanics. So delta theta equals the initial angular velocity multiplied by time plus half alpha t squared. This is the equivalent to the equation S equals u t plus half a t squared. And you see we just replaced the u with the omega and the alpha with the a, and the displacement with the angular displacement. So this equation, usually when you use it, you'll probably find that omega initial is not, there's no initial velocity, so the equation will be simplified to delta theta equals half alpha t squared. And if you have alpha and t, you'll be able to get delta theta. Now on to the final Savat rotational equation, states that the final angular velocity squared equals the initial angular velocity squared plus 2 alpha delta theta. Its equivalent in normal mechanics is v squared equals u squared plus 2as. This is also one of the ones that you use a lot, probably. It's basically the same. If you know how to apply normal Savats, you'll be able to know to apply it in rotational mechanics, because you'll be given everything, probably. And one thing you must know, in normal savants we state that in order to use these equations, the acceleration must be constant. So in the rotational mechanics, it's exactly the same, but the angular acceleration is the thing that has to be constant. If it's not constant, you cannot use the equations to find omega, theta, or time even. Now on to Newton's laws in rotational mechanics, or forces in general. This is the equivalent of topic 8.2 but in rotational mechanics. As we stated in the beginning, torque equals force times r, distance from the pivot point. Now, since torque is the force equivalent in rotational mechanics, we also have a mass equivalent in rotational mechanics. This is known as the moment of inertia, denoted by I. It is equal to mr squared, where r is also the distance from the pivot point and m is the mass. But here's something different. Something or a rotating object might have many moments. So we have sigma, showing that the moment of inertia in total is the sum of moment of inertias, or I equals mr squared plus mr squared plus mr squared again. So how many objects you have, each one will have its own moment of inertia. So don't add up the masses and multiply it by the radius squared. This will give you the wrong number. You have to calculate each moment of inertia of each object separately, then add them at the end. Another important thing you have to know, that sometimes an object's moment of inertia is not just mr squared. It may be equal to, for example, 2 over 5 mr squared. But don't worry, if it's different from the one in the data booklet, which is I equals mr squared, in the question you'll definitely be given the moment of inertia of the object. So you don't have to worry about that. Now, since let's talk about Newton's laws. We know that force is equal to mass multiplied by acceleration, right? And we know that force in the rotational world is torque. And you know that mass is the moment of inertia. And you know that acceleration is alpha, the angular acceleration. Now we have an equation, torque equals I alpha. This is exactly as Newton's laws, but applied in rotational motion. Torque, the force, equals a mass, which is moment, and multiplied by the acceleration, which is the angular acceleration, which is also given in Newton meters. Now on to the final thing. We have momentum. Momentum in the rotational world is denoted by the letter L, and it is equal. Let's start with Newton's law. The momentum is equal to the mass times velocity. So it's product given in kilogram meters per second. So L, the angular acceleration, as we stated, we know that mass is equal to I in the rotational world, so we have I. I know that velocity is equal to omega. So there we have it. L equals I omega. This is given, I think, in kilogram meter per second squared. Now we on to another equation. We also know that force equals the change in momentum, so delta P over change in time. So you could say that the change in momentum, which is referred to as impulse, equals F delta T. So let's replace what we know in the rotational world. Delta P is delta L, F is torque, and delta T stays the same. So the change in the angular velocity or angular impulse is equal to torque multiplied by the time, the change in time. But we also have another equation for angular impulse. It states that delta L equals delta I omega. But yeah, here, so since probably the angular moment of inertia won't be changing, it would be written as I delta omega, where I, of course, is the mass equivalent at the rotation world in the moment of inertia, and omega is the angular velocity. Finally, in the rotational world, of course, conservation of energy also applies. So we have the equation for kinetic energy in rotational terms. So the rotational kinetic energy, let's say it's EKR, so you don't get it confused with translational kinetic energy, equals half I omega squared. And it is also equal to the momentum squared over 2I. If we write the one for translational motion, it is half mv squared, which is equal to p squared over 2m. As we see here, it's exactly the same, but things are replaced. The moment of inertia is replaced with the mass, omega is replaced with velocity, and the momentum, angular momentum, is replaced with translational momentum, and again, moment of inertia is replaced with mass. So that's it. Now I'm done explaining. Let's go ahead and start answering our first question. Let's see here. Question 1. A 1-meter ruler is balanced, on a 30 centimeter mark by placing mass. Sorry, this is the wrong question. Sorry, just ignore that. Let's actually solve a past paper question. So, many times in the IB syllabus, they'll also ask you to convert from rotational to mechanical. So this question, I'll use it to explain to you how to convert something from rotational motion to mechanical motion. So the question gives us a ball. Sorry. It sits on top of a right angle, height h. The ball has radius r. As this we know this is the right angle. It is also given that the moment of inertia is 2 over 5 mr squared. And the question is telling us that show that the linear velocity of the sphere as it leaves the slope is the square root of 10 gh over 7. So you look at it, you feel scared, of course. So let's say, so at the top you have potential energy, EP, equals mg delta h. And on top you're at rest, so you don't have any kinetic energy or rotational kinetic energy. But at the bottom, that potential energy will be converted to both rotational and translational kinetic energy. So you now have to equate all three. So EP equals EK plus EKR, which is rotational kinetic energy. So first, let's write down the equations. mg delta h equals half mv squared plus half I omega squared. So now, in order to solve this equation, we must have everything in standard, in translational form. So we have to convert I into 2 over 5 mr squared. We also have to convert omega into V over R. And since it's squared, it will be V squared over R squared. This you should be able to know from topic 8.2, where we talk about circular motion. Omega is equal to V over R, and just to state further, the acceleration is also equal to, or the angular acceleration, sorry, is also equal to the acceleration divided by the distance from the pivot. These things you have to know, because sometimes the equations in the data booklet won't help you. So now let's substitute. So mg delta h, still the same, equals half mv squared plus half multiplied by 2 over 5 mr squared multiplied by v squared over r squared. So let's simplify. Mg delta h equals half mv squared plus, so half times 2 over 5 is 2 over 10 mr squared multiplied by v squared over r squared. Sorry. So now we have r squared. So when you multiply r squared by 1 over r squared, they cancel out. So it's going to be like that. So mg delta h equals half mv squared plus 2 over 10 mv squared. So we need to have a common denominator here. So we have to multiply this by 5 on top and bottom. So it's going to be mg delta h, still the same, equals 5 over 10 and mv squared plus 2 over 10 mv squared. So if we add mg delta h equals 7 over 10 mv squared. And now it's telling us, of course, we need to rearrange for the linear velocity. So v, since we have mass on both sides, we can cancel it out. So it's going to be g delta h equals 7 over 10 v squared. So rearranging for v, v squared equals 10 g delta h over 7, and v finally equals the square root of 10 g h over 7, which is what they want us to show in the question. So here, in this question, you learned how to convert from rotational form to translational form. And this question is actually quite common in paper 1, actually, which is kind of sad since the question in front of me is actually a 3-point question and it took a lot of time. But yes, you have to be able to try to convert from rotational to translational form in order to equate energy or even other forms. Let's go ahead and solve another question. I'm just trying to find an easy question for now. Okay, this is a harder question that you have to visualize a little bit. A children's roundabout consists of a disc rotating of radius 2 meters. So what I like to do is write down everything given. So it says radius of 2 meters, r equals 2, and mass of 100 kilograms, mass equals 100 kilograms, and a handrail of radius 1.5, and mass, mass again equals 20. So he's giving you this because, as I stated earlier, everything has a separate moment of inertia, so you're taking the sum. So probably the 2 meters and the 100 gram have a moment of inertia, and the others also have their own moment of inertia, and the total moment of inertia will be their sum. So the first question states, ignoring the structure supporting the handrail, okay, calculate the moment of inertia of the roundabout. So it's basically telling us to ignore R equals 1.5, M equals 20 for now, and calculate the moment of inertia of the roundabout. So we stated that the moment of inertia equals mr squared, and since we are given, we're just gonna substitute. And here it doesn't state anything about different numbers such as 2 over 5 or 1 over 4, such in like the last question. So we're just gonna use the one in the data booklet. So it's gonna be 100 multiplied by 2 squared, which will be 400 kilogram meters squared. This is an easy one. B. The roundabout is set in motion by pushing the handrail with a force of 200 newtons for a distance of 1 meters. This is repeated 10 times. Calculate the torque applied to the roundabout. So we know that torque equals force multiplied by radius. Since radius is 1, it will be equal to the force applied, which is 200 Newton meters. The work done each time the roundabout is pushed. So this is a kind of hard question, and you have to be able to think about translational motion and equate it to rotational motion. So we know from topic 8.3 that the work done equals the force multiplied by displacement. Correct? So here, a torque of 200 Newton meters is applied 10 times. Correct? So let's just write it down. Torque equals 200, and it's applied 10 times. So, oh yes, I know. So here we actually won't be using this equation, we'll be using the equation for kinetic energy, half I omega squared. So I'm assuming in this question that they want the whole moment of inertia of the whole object. Since we already calculated the moment of inertia of the roundabout excluding the handrail, we already know it is 400. So I equals 400, then plus the handrail of moment of inertia, which is half, multiplied by its mass, which is 20, multiplied by the distance from the pivot, which is 1.5 squared, and using our calculators, sorry, and using the calculator, I think 2.25. Let's get my calculator 1 second. Sorry, guys. So 400 plus half times 20 times 1.5 squared. And remember to put them in brackets because the calculator can get confused. 0.5 times 20 times 1.5 squared. It will be equal to 422.5. And in physics, we stay with 3 significant figures. So we're going to round it up to 423 kilogram meters squared. Since now we have the moment of inertia, we can calculate. No, we actually don't have omega, so we will not be able to calculate the work done. So we stated the work done is equal to force multiplied by displacement. So in translation form, that would be equal to torque multiplied by the angular, but we don't have that. Oh, we actually do. We actually do. The work done is simply force multiplied by displacement, and the force here is 200 newtons. Displacement is simply 1. So the work done is 200 joules. So this is a common misinterpretation here. Like I just did, I didn't know how to convert from rotational motion to translational motion. I was kind of confused here. I didn't know how to get the work. I didn't know what work he was talking about. So this is a common question where they switch from translation back to rotational and back again to try to confuse the student to see how well he knows his things. Sorry, I'm just trying to get the question. Okay, let's go on to the other question. Let's go here. I'm just looking for an easy question here. Okay, this question is one of the questions I saw on my exam. So it states that a uniform rod of weight 42, so let's just write down the knowns 42, and length of 8 meters is positioned horizontally. The rod is hinged at its right end and supported at a point 6 meters from the frictionless pivot. So here, this is the support, let's say, and this is distance is 6, and this distance is 2, so the bigger distance is 8. And this is, it's telling you this is the pivot. So this is the center of mass technically here. So any distance or the R here is distance left of the pivot, of course. So question number 1 states, calculate the force the support exerts on the rod. Well, this is simple. In rotational motion, since this object is in equilibrium, we can say that the sum of torques is 0. So the torques are equal. So first, let's calculate the torque of the object itself. So the object has a weight of 42 newtons and the support is 6 meters away. So 42 newtons. So sorry. Torque equals Fr, which is equal to 42, which is the weight with also force, multiplied by R. R here is 6, so it is equal to 6 times 42, 252 Newton meters. Let's see. And it is correct. On to the other question. Let's solve a paper 1 question. Since it actually comes up a lot on paper 1, not much in paper 2, let's solve. Oh, there aren't any. Okay, a yo-yo of mass m, radius r is released from rest and allowed to fall vertically while unwinding. If its moment of inertia is I equals half mr squared, so it's given here that it's half mr squared, what is the linear acceleration of the center of mass? So this is actually a hard question here. So I'll write down my knowns. We have mass, we have r. So we know that torque equals I alpha, correct? And alpha here equals to A over R. And since here we're talking about gravity, it will be equal to G over R. So substituting in the equation, torque equals I G over R. Yes, so here this is force times radius, Fr equals Ig over R. Cancel out. Oh, sorry, no, they don't cancel out. So unwinding moment of inertia is half. What is the angular acceleration of the center of mass? What is the linear acceleration of the center? So it's a complex question. Okay, wait 1 second. So you have the moment. So it's not, you don't use the Savat equations here since he's given you the moment. Uh, let's think for 1 second here. There's something I forgot. We're talking about actually three forces here. So we have, since there's a string attached, you have tension, T, that's denoted by big T. Then you have the force of gravity, mg, then you have the net force, which is ma. So we have to create an equation ourselves. Ma, the net force, equals mg minus tension. And since we have it here, ma equals 0, or is it equal to 0? Yes, so we have ma here equals mg minus half mr alpha, and since a equals r alpha, so a equals r alpha, so we have mr alpha plus half mr alpha equals mg. We can cancel the masses. 3 over 2 r alpha equals mg, so g will be equal to 3 over 2. 2 over 3, sorry. The acceleration will be equal to 2 over 3, and it gives us C. On to another question. It states a plank of mass m, 8, of mass 8 kilograms and length 4 meters rests horizontally on two supports placed 0.5 meters from each end. So let's try to visualize it right here. Sorry. So this is 4, and it's telling you 0.5 centimeters from each end. So a support here and another support here, and this distance is 0.5. This is also 0.5, given this distance is 3. So it states a person of mass 60 kilograms walks from the center toward one end. So he's walking either left or right, doesn't matter. At what distance from the center will the plank begin to tip? Very nice question. So he's walking towards one end. So intuitively, you'd know that actually it won't start to tip until he reaches 0.5 centimeters. So he reaches either here or here, based on which direction he's walking. Intuitively, even if he's here, it will never tip. Until he reaches here, it will start to tip. So, at what distance from the center? Well, this is 0.5. This distance is 3. So this is 1.5. Each of one of them is 1.5 from the center. Correct? Each of them is 1.5 from the center. So intuitively, at exactly 1.5 meters, which is exactly the point after the support, so you're moving after the support here, the plank will start to tip. And this is just an intuitive question, it actually doesn't require anything. And the answer 1.5 is actually one of the answers given. So here, if you want to use the process of elimination, you can use. So its first answer is 1 meter, which is completely wrong since 1 meter will probably be somewhere here. 1.3 meters is also another answer, which will also be somewhere here. So both are wrong. So now we have 1.5 meters and 2 meters. So let's see 2 meters. 2 meters is exactly at the edge. Which, if you think about it, it probably won't start. It's telling you start tipping. Exactly at the edge, the thing will probably just completely flip, not start tipping. So the only actual answer here is 1.5 meters. So the final question today. A rod of length L and the mass M is pivoted at one end and released from rest in a horizontal position. What is the angular velocity just before it strikes the vertical? This is a very, very bad question, guys. It's probably a question where one of my teachers put it on the exam and literally nobody answered it. So you have to actually start uh, visualizing it. So it's impossible to answer without visualizing. So a rod of length L is pivoted at one end and released. So just like this, this is the pivot. And what is the angular velocity just before it strikes the vertical? So this is the vertical here. So as you see, it's just basically telling you it has rotated 90 degrees or pi over 2. So what is the angular velocity? Well, since he's giving you the length and mass, you know you're not going to use the Subat equations, so delta theta. But actually, wait 1 second. We'll be using torque. So let's think here. We'll be using the conservation of energy actually. Oh, this is very bad. Okay, let's think here. This is distance L, okay? And this is also, it doesn't matter what distance this is. So you have to think that after it rotates pi over 2, it is actually dropped a length of L over 2. So the kinetic energy, the change in kinetic energy is equal to mg delta H. Delta H here is equal to L over 2, so mg L over 2. Oh my god, this is a very bad question here actually. So now, since we know how to equate, and there's no translation kinetic energy here, so equate this to the equation for rotational kinetic energy and expand in terms of translational things. So mg L over 2 equals half I omega squared omega mg L over 2. And it's actually asking about the angular velocity, so you won't have to expand on it. But for the moment of inertia, you'll have to do half times ml squared in this situation, since it's telling you it's denoted by L, so it's going to be like this, omega squared. Now you start canceling. So, sorry, and the masses here will also be big M. So here you can cancel both m's, both sides. You can also cancel the square on the L to the right and cancel the L. So it's giving you G over 2 equals half omega squared. Oh, wait one second. Oh, no, sorry. It's not half omega squared. It's half L omega squared. So you cancel also the half. So G over L under the root equals omega. Omega, sorry. Oh, wait a second. So it's the wrong answer. So, yes. So, this is actually the right answer, but in the question, it does not state actually that the moment of inertia equation is 1 over 3 mr squared. So, actually, if you account for the factor of 3, the equation will be 3 over 2 GL. But intuitively here, the actual question is wrong. They have to give you the equation for moment of inertia. If they do not, you must use the one in the data booklet, which is mr squared. So the actual answer, given what we have, is G over L, root G over L equals omega. And thank you guys. This means we have covered one of the many complex topics that I think I and many other students struggled with in the IB physics syllabus. I hope you start answering some questions, and I would like for you to even read about it. Uh, if you're looking for an IB physics book, I would recommend the Pearson book for you, since it has exercise questions for people who don't understand that much, and this then has chapter questions to challenge you more. Since actually rotational mechanics wasn't in the last syllabus as a normal topic, it was actually a rotational option, and this is a new syllabus, of course, starting for 2025. So you won't find any past paper questions, but if you want to challenge yourself, the best thing you would do is find past paper threes, yes, paper threes, and paper three is consists of four options. The option called engineering physics is the topic you want to answer questions on, as will be the exact same thing. You won't find anything out of topic. The data booklet will help you with everything. These are the types of questions you want to answer before going to the exam, because they're in IB form. But I would also recommend try to answering questions like this one, where you actually don't have any numbers, because this comes up a lot, and I mean a lot, in paper one, where they just want you to rearrange an equation without any numbers. And now we are done with the first additional higher level topic, in the IB physics. This is again topic A.4 in the IB physics syllabus. It is rigid body mechanics. So thank you guys.